Hello there. In this video we're going to continue our discussion of probability density functions in two variables, which you can extend to higher variables if you wish. So in the previous video we discussed and proved that this function f of xy equals 3 halves x squared plus y squared on the unit cube, or unit square, is a probability density function on variables x and y. So to prove that, what we did was show that the double integral over the domain of this function fxy dx dy was equal to 1. And of course, trivially, this function fxy is greater than or equal to 0 on this domain D. X squared plus y squared is always a non-negative number on any real subset, as long as x and y are not complex, which it's not. So these two functions definitely do satisfy. In addition to that, we proved a couple other things, namely, the marginal density function for a random variable x was equal to 3 halves x squared plus 1 half, which we found by taking the integral over the support of y of fxy dy. And we also found the marginal density function for a random variable y, and we found that to be equal to 3 halves y squared plus 1 half via either this property, integral over the support of x, of fxy dx, or by observation that this function was symmetric in terms of its variables. So in this video, we'll calculate the mean, second moment, and variance of these random variables via this probability density function in two dimensions, and also discuss another property as well. Alright, so let's begin by calculating the mean, or the expected value, of a joint density function. So the expected value, or some people write mu x, is defined to be equal to the integral of the support of random variable x of x times the marginal density function of random variable x dx. This definition is practically the same exact thing as the single variable case, except that this function is the marginal density function of a multivariable PDF. But overall, the calculations will not be different. Similarly, the expected value of y, which some people write as mu y, is defined to be equal to the integral over the support of y times the marginal density function of y with respect to y. So let's do this. They're both the same function, just symmetric in their variables. So let's just find this y value since it's pretty much here and convenient. So this is going to be equal to the integral from 0 to 1. So remember, this is the bounds for the y values of y times 3 halves y squared plus 1 half dy. So this is going to be equal to the integral from 0 to 1 of 3 halves y cubed plus 1 half y dy. So using your fundamental theorem of calculus, that's going to be equal to, so y is going to go to a power of 4, and 4 times 2 is 8, so we have 3/8 y to the 4th, plus then we're going to have 1/4 y squared as y goes to 1 and as y goes to 0. So as y goes to 1, we're going to have 3/8 plus 1/4, and 0 doesn't go anywhere, and that's going to be equal to 3/8 plus 2/8, which is 5/8. So that's the mean of y. Now, since the variables are symmetric in distribution, one can also find that mu x also is equal to 5/8 as well. So now let us move on to the second moment, and you probably can guess how this is going to be defined. So the second moment for x is going to be defined to be equal to the integral over the support of random variable x of x squared times the marginal density function of x with respect to x, and similar for y. So let's just calculate this out. So that's going to be equal to the integral from 0 to 1. So remember, that's the domain of random variable x of x squared times the marginal density function of x, which is 3 halves x squared plus 1 half dx. Distributing our x squared in, that's going to give us the integral from 0 to 1 of 3 half x to the 4th plus 1 half x squared, integrate with respect to x. So that's going to be, so increase the power by 1, so that's going to go to 5, and 5 times 2 is 10, so we have x to the 5th, plus, so x is going to go to the power of 3, 3 times 2 is 6, so we have x cubed. And now we're going to send x to 1, x to 0, and subtract. 0 goes to 0, so no big deal there, and as x goes to 1, we're going to get 3/10 plus 1/6. So what is that going to be equal to? So we can multiply, I don't know, you can work out the details. What is that? 7/15, I think? Yeah. So that's going to be 7/15. So that's the second moment of random variable x, I believe, right? So yeah. So we can multiply this by 6, multiply that by 10. So we get 28 divided by 60. Yeah, that's fine. Also, since x and y are symmetrical about their variables, we're going to have y squared is going to be equal to 7/15 as well. All right, so let's find our variance. That's also not too hard to find. So the variance of x is going to be equal to, so remember, this is going to be equal to the second moment minus the mean squared. So that's going to be 7/15 minus 5/8 squared, which is going to come out to 73/960 once you get a common denominator. And also remember the variables are symmetric, so this is also equal to sigma y squared as well. If you want to take the square root to get the standard deviation, you can do that if you want. That's going to come out to approximately 0.076 if you prefer decimals. Now, another calculation that is often done when you have multivariables is what we call the product mean or the product moment, depending on who you talk to, or just EXY. So EXY is defined to be equal to mu XY as alternative notation, and that's going to be defined over the support of your function of XY multiplied by the probability density function fxy dx dy. And also note that some people write dx times dy as instead ds for the support. So let's calculate what this number is. So mu xy. So this is going to be equal to the integral from 0 to 1, integral from 0 to 1, that's my y integral, that's my x integral, of xy multiplied by 3/2 multiplied by x squared plus y squared times dx dy. So I'm going to pull my 3/2 out, as I have, because it's just my preference. So 3/2 times the integral from 0 to 1, integral from 0 to 1. And I'm going to distribute my x, y in as well. So that's going to give me x cubed y plus xy cubed dx dy. I'm going to begin by focusing on my x integral here. That should be capital Y, always. So this is going to be equal to 3/2 times the integral from 0 to 1. So I'm integrating with respect to x, so that's going to turn into 1/4 x4y plus 1/2 x squared y cubed. As x goes to 1, x goes to 0 dy. So that's going to give us 3/2 times the integral from 0 to 1. As x goes to 1, pretty much the x's disappear in some way. So 1/4 y plus 1/2 y cubed. And as x goes to 0, they cancel out the terms completely. So we're just left with that dy. So now we're going to integrate with respect to y. So that's going to give us, so y is going to increase to a power of 2. So we're going to have 1/8 y squared plus y is going to increase to a power of 4. So that's going to turn into 1/8 as well. Y is going to go to 1. Y is going to go to 0. So that means mu xy is going to be equal to 3/2 times 1/8 plus 1/8 is going to be 2/8, which is 1/4, which is going to be 3/8. All right, so one may ask, what is so special about this number? So you may remember the following property, that EXY is equal to EX times EY if XY are independent. So if x and y are independent, then this is true. So this is one way to test and see if they are not independent. And I'll explain what that means in case you're not familiar with the logic associated to that process. But nonetheless, mu x is going to be equal to 5/8, as we have already calculated. Mu y is going to be equal to 5/8, which we calculated. And mu xy is going to be equal to 3/8. One can see that mu x times mu y, which is going to be equal to 25/64, is not equal to mu xy, in this case is 3/8. So these are not equal, therefore we can assume we've actually proven that x and y are not independent. Because if they were independent, then this would be true. But just as a side note, you have to remember that the converse is not necessarily true. So important. So if mu x times mu y is equal to mu xy, then xy are not necessarily independent. Because remember, the product of x, the probability of x times the probability of y must be equal to the probability of xy for all possible values x and y. Just because the mean products are equal to the product moment, it doesn't necessarily mean that it's true for every probability. So just because mu x times mu y would be equal to mu xy, that doesn't imply that they are independent, but they could be. But if you prove that mu x times mu y is not equal to mu xy, that guarantees that they are not independent. So these are just some side notes on joint probability density functions, and also how you calculate the first moment, second moment, and the variance of these random variables. Hope you enjoyed.